We're now going to extend our knowledge for Venn diagrams with 2 sets to add a 3rd set. So we can still do a lot of the same things before. It still makes sense to do all these set operations, but now we're going to be working with a 3rd set. Now the problem with this is it does get a little bit complicated because there's a lot going on. So when I draw my Venn diagrams with 3 sets, I still draw my Venn diagram as before with my circles A and B, and there's that overlap between them. But now what happens is I need a 3rd set that potentially intersects with both A and B, but also has its own individual sections as well. So really we have a lot more regions going on. When it was 2 sets, there were only 4. There was the stuff in common, the stuff unique to each set, and then the outside. But here we have a ton. So we normally label these regions with Roman numerals. This is our first region. This is our second region. So region 2 would just be the stuff unique in common to A and B, but not C. The 3rd region is over here. The 4th region and 4 in Roman numerals is IV. The 5th region is the stuff in common to all 3 sets. 6 is the one right next to it. 7 is the stuff that's unique to C. And then we have the outside region, which is 8. Okay. So you're going to see in your homework and everything, it's going to label these with Roman numerals for your own personal homework and stuff while you're trying to go through it. If you just want to label these 1, 2, 3, 4, 5, 6, 7, and 8, that's perfectly fine too. Okay, so it gets a lot harder to talk about what these regions are in terms of like intersections, complements, things like that. So before with just 2, this section was the intersection, but now it's also some other components too. This is just the intersection of A and B and not in region C. This stuff is what's in common to A and C, but not in region B because it's outside that circle. So I'm going to try to describe some of these things, and at the very end we'll go ahead and we'll try to figure out, can I actually give a description using set operations for particular regions. So to start out, let's go ahead and label these numbers. Again, just to make it a little bit easier, I'm going to use regular numbers instead of Roman numerals, but you could easily make these Roman numerals. If I talk about this section right here, region 5. And 5 in Roman numerals is a V. This is the overlap of all 3 sets. So the way we could write this one would be the intersection of A, B, and C. They're in A, and they're in B, and they're in C. Okay? So the elements here are in A, B, and C. Remember that intersection represents end. If I instead talk about the union of the 3 sets, okay. If I look at A union B union C, it still does the same thing where it's going to meld all of the 3 sets together. So here's a circle that gets filled in. Then we add in B circle that gets melded to this one. And then last but not least, we meld in C circle and it gets added in. So regions 1 through 7 would be the union of the 3 sets. So here, the elements here are in A or B or C. Okay. So this one's actually really helpful if I go then to talk about region 8, which is the outside. So it's everything except regions 1 through 7. So if you think about what that means, it's the complement. So let's go ahead and label these. So region 8 which in Roman numerals would be VIII. This would be the complement of the union. So I take the union of the three sets and then I find the complement. Because again, these two things should fill in the entire U, okay? And they do. So the complement of A union B union C is everything not in the union. So not in A or B or C. Okay. So when you go to create a Venn diagram with multiple steps, you still should follow the same process. I'd always recommend starting in that middle section because it's easiest to see the overall overlap. And then you kind of work piece by piece. Then you go ahead and match up A and B. Okay, is there anything in common to just those two? And that goes in region 2. And then you keep following that process. So we're going to try an example with that. We want to construct a Venn diagram illustrating the following sets. So we have our universal set U, which is a ton of different Disney movies. And then we have these 3 subsets, A, B, and C. And so what I want to do is I want to fill in my Venn diagram. So I'm going to go ahead and zoom out a bunch to be able to fit this all on one screen. So again, I always want to start right here in the center. So I need to go ahead and look at these 3 sets and see, is there an overlap? And if I look, the word Bambi is in all of them. So I'm going to go ahead and cross Bambi out of the universal set because that will go right here in the middle. Okay. Now I want to go ahead and I want to move on to any one of these just smaller intersections. So starting in this region here, which is region 2, I want to see, is there a movie in common to just A and B? So looking at these remaining movies, there is something they share in common, and that's the movie Hercules. So I'm going to go ahead and I'm going to cross off Hercules from my list. That needs to go right here. Okay. Then we do the same thing. If I look at this section next, this is the overlap of the circles B and C, but it's not in A. So I need to go ahead and compare these two and see, is there something in common? And indeed, they both share tangled. So I'm going to go ahead and mark tangled off. And that's going to go right here. Okay. And then our last intersection of circles is the stuff that's in common with A and C, but not in B. So I need to compare these 2 sets. And looking at what's left, the only word they share in common or movie is going to be Pocahontas. So we're going to go ahead and mark Pocahontas off. And that's going to go right here. Okay. Now I can fill in these last pieces. So this section here is the stuff that is unique to A. And the only thing that hasn't found a spot yet is Tarzan. So we go ahead and mark Tarzan off. That's going to go right here. Moving on to B, Mulan has not found a spot yet, so Mulan is unique to B. So we go ahead and mark that off. Okay. Then looking at set C, Frozen is the last one remaining. So that goes here out to the side. Ran out of colors, but that's okay. So we'll just start repeating them. So Frozen goes on the outside. So sets A, B, and C are all filled up. And again, so you can easily see, this is a circle, and those are the 4 movies that belong to A. Likewise, this is B circle. Hercules, Mulan, Bambi, and Tangled are the 4 sets in B. And then looking at set C, that's Bambi, Tangled, Frozen, Pocahontas, the 4 sets that we have in here. Okay. So the only thing that hasn't found a home yet is Cinderella, Dumbo, and Up. So the 3 of those need to find a spot. So those just go on the outside. And so you can fill them in wherever you can fit them. Cinderella is kind of a long word, so let's put that down at the bottom. So we've got Cinderella, Dumbo, and Up. Okay. So this is our Venn diagram for these 3 sets. And again, now you can do operations. So if I want to take A, intersect B, intersect C, this is in the intersection of the 3 sets. If I just ask for A intersects C, then I'm going and looking at just the overlap of these 2 circles. So the intersection of A and C would be Pocahontas and Bambi. If I want to find a complement, I go ahead and shade out A, and then everything left over, which is Mulan, Tangled, Frozen, Up, Dumbo, and Cinderella, would be an A complement. So you still follow the same approach for all of these, okay? So what happens is now, because I have a lot more sets and a lot more things I could do, I could talk about these regions using a lot of different methods and a lot of different operations. So what we want to do now is we want to see if we use Venn diagrams, can we determine if the following sets are equal for all sets A, B, and C? So basically what I'm asking here is if I do this operation and if I do this operation, do they end up resulting in the same thing no matter the elements that are filled inside here? So essentially I'm asking at the end of all this, what regions in my graph am I talking about? So again, I'm going to go back up here. This is the Venn diagram we made for these 3 specific sets from that universal set. So if I take A intersects C, it's Pocahontas and Bambi. But maybe if I do different operations, it still ends up talking about this exact region, which is 4 and 5, and it would still result in Pocahontas and Bambi. If that's the case, I would say they're equal because, again, they give me the same thing at the very end. So what I want to do here is I want to figure out, if I go through these operations, which areas would I end up listing the elements from? So my first step in this problem is to find the regions and it could be one region, it could be multiple, in A union B intersect C. Okay. So what I like to do for these is I like to draw a picture. And I'm going to take it basically piece by piece. Let's see if it'll do it. There we go. Good enough. Okay. So we have our set A here. We have set B here. And then we have set C here. Okay. This is our universal set, and then we have the regions 1, 2, 3, 4, 5, 6, 7, and 8 is on the outside. Now I am going to have to use this picture a few times, so again, I'm going to cheat preemptively. We're going to need it again down here, and then I'm going to need it twice more for the next problem as well, because we're going to do 2 of these. So we'll preemptively copy them. Okay. All right. So what I like to do is I like to list the set and then list the regions. So this way I can kind of keep track of everything going on. And then ultimately you can draw a picture for this or multiple pictures. But again, I'm going to go through my order of operations, and the first thing I should do is start in parentheses. So I want to figure out when I find B intersects C, which regions would I be listing the elements from? So based on my picture, B intersects C would be this overlap here. So it would be regions 5 and 6. So anything that I would have listed inside that section and inside 6 would be in this set. So in the case back up here, B intersects C would be Bambi and Tangled. Okay. Now I want to join this with set A. So again, it's up to you how your brain works. If you like the more solid approach like this, absolutely. If you want to shade in the picture, absolutely. So now I need to figure out what is set A. So looking at A's circle, I'm going to list all of the regions that fall inside it. So that would be regions 1, 2, 4, and 5. Okay. And now I've got this set, I've got this set. We want to union them. So that means I'm just joining these two together. Okay. So using the chart, all you do is meld this into one list. So you get all of these numbers plus all of these. So my union would be 1, 2, 4, 5. And the only extra one that's really added from here is 6. So these would be the 5 different regions that this particular set overall would talk about. But again, you can do this just directly from the picture. You don't need to make this chart. So again, I start with B intersects C. That's right here. I'm going to union it with A. So if I shade in A set, that would be this region here. And union just melds the two shaded regions together. So my union is 1, 2, 4, 5, 6. Exactly the same thing. Okay. So regardless of the actual elements in the Venn diagram, my end operation would be all the elements that are listed inside this region. And I don't know why this suddenly unshaded. So we'll go back to that. Okay. Now what I want to do is the same exact thing with this second step. So I'm going to see what regions does this talk about. And that will tell me, do they actually equal each other or not? Okay. So my second step now, can move this up a little bit, is to find the regions in A union B intersect A union C. All right, so we're going to do the same thing. We'll do it with a chart, but we'll also use the picture. So I always got to start in my parentheses. So I'll start by finding A union B. So using my graph, set A is right here. And set B adds in these pieces. So my union talks about the regions 1, 2, 3, 4, 5, and 6. Now I need to do the same thing here. I need to find A union C. So again, set A is still the same thing. It's 1, 2, 4, and 5. Now adding in set C would be down here. So ultimately the regions in this would be 1, 2, 4, 5, 6, and 7. So I'm now looking at the intersection of these two sets. So using the list, you're basically finding the numbers in common. Using the picture, you're looking where does the shading overlap? And that would be exactly here. The pink and the blue have overlapped and formed this purple region. So this is the double shaded area. But using our chart, 1 is in common, 2 is in common, 4 is in common, 5 is in common, and 6 is in common. So that is the overlap and ultimately the intersection. Okay? So in the very end, these two sets end up being exactly the same regions. So because that happened, you end up with the same thing. We can say these sets are going to be equal to each other. Okay? So since each set represents the same region, or it results in the same region, these are equal. So indeed, we can say A union B intersects C is exactly the same as A union B intersect A union C. Okay. All right. This is really just like the distributed property. You're basically distributing A union to this, and then you're distributing A union to this, and taking that intersection afterwards. Okay. So let's try another one of these. In this case, we'll hopefully come up with the opposite situation where they're not actually equal to each other. So I can't say this. So what I want to do is the same process. I'm going to go ahead and find the regions this talks about, find the regions that this one talks about. Okay. So again, let me get prepped up for this. Give myself some space. Okay. And so let's start with our first set. So I'm going to find what is A union B intersects C complement. So this one's a lot messier, a lot more going on. Again, following my order of operations, I've got to begin in parentheses. So I need to figure out what is B intersect C. So if I look at these two circles, here is B, here is C. So their overlap is the regions 5 and 6. Now I want to take the complement of this. So if I take the complement, it's everything except 5 and 6. So if I shade that in, it is everything on the outside of that. Trying to make it as clean as possible. So I no longer need that region here. So my actual set that I'm talking about is 1, 2, 3, 4. Not 5 or 6. So then 7 and 8. Okay. Now I'm going to end up joining this with A. So if you feel comfortable just jumping into that, go right ahead. If you want to write down A sets, because again, you like this approach instead of just shading in the picture. Circle A is 1, 2, 4, and 5. Okay. So now I'm taking the union of these two things. So I'm really just melding this together to one list, or using my shaded diagram. It is anything shaded in here. So the only thing I'm not including is region 6. If I go ahead and do my list, I get all the numbers 1, 2, 3, 4, 7, 8. 1, 2, 4 are already in there, so you're just adding in the number 5. So this ends up being 1, 2, 3, 4, 5, 7, and 8. So this set would list a lot of elements potentially. Okay. Now I'm going to do exactly the same thing with this set. So I need to figure out what is A complement intersect B complement union C. Okay. All right. So going through the same process, I'm going to start in those parentheses first. But to be able to do this union, I've got to take care of that exponent spot. So I need to figure out what is B complement. So in that case, I go ahead and I black out B's circle. And so the complement of B is everything out here. So it is 1, 4, 7, and 8. So I no longer need that shaded bit. So that's 1, 4, 7, 8. Now I'm going to join that with set C. So again, you don't need to write what C's set is, but that's fine if you want to. Set C is 4, 5, 6, and 7. Now we're going to go ahead and join these two sets together and meld them as one. So it's really anything that's shaded. So all of the numbers except 2 and 3, those haven't been shaded. So that gives me 1, not 2, 3, 4, 5, 6, 7, and 8. And again, that just melds this list together. So 1, 4, 7, 8. 4 and 7 are there, so you're just adding in the numbers 5 and 6. Okay. So I've got the regions this set talks about done. Now I need to intersect this with A complement. So before I can find the intersection, I have to figure out what is A complement. So I'm going to start just getting rid of that. A complement blacks out this region. So that would be all of this stuff on the outside here. Okay. So A complement is 3, 6, 7, and 8. Now I can go ahead and I can take the intersection of these two things. Okay. So just to refresh, if I shade in, let's do it in blue, this section here, that's region 1, region 4, region 5, region 6, region 7, and region 8. So everything on the outside of these gets shaded too. You are looking for the overlap of these two sets. So you're looking where it is that shading mix. And really, 6 is the only spot that's shaded, 7 and 8. These are the 3. And looking at our list, 6, 7, and 8 are the only things in common. So after I go through this operation, I end up with region 6, 7, and 8. So if I go ahead and compare these two, they are very different sets that I end up talking about. They're different regions. So there's no way that these can be equal to each other. Okay. So here, since we don't end up with the same regions, these are not equal. So what I would write is A union B intersect C complement is not equal to A complement intersect B complement union C. They are not the same. Okay? So we have just a little bit left in this section. the very first thing kind of results from doing this process, and it's something called De Morgan's laws. So De Morgan's laws is another name you're going to see later on when we do logic, but it's a really nice technique that can just kind of make your life a little bit easier in some certain circumstances. So what you can do is if you need to take the union and the complement, or the intersection and the complement, this again is treated like an exponent. So if you think of your exponent rules, it distributes down to each of those pieces. And that is going to be true here. If I want to evaluate A union B complement, instead I can go ahead and distribute that complement piece. However, in this case, it also ends up distributing to the operation. And so it does the opposite, because remember, the complement means the opposite essentially. So this would distribute and become an intersection. And likewise, if I take the intersection, when I distribute this to all three things, you get A complement, this flips to union, and then you get B complement. Okay. So the benefit of doing this is it's really nice when you have a ton of complements going on. Like if I asked you to find A complement, union, B complement, and then take the complement, you'd have to find these two sets first, then take the union, and then take the complement. What ends up happening with De Morgan's law is you would distribute the complement. So you would take A complement, complement. This would become intersection. And then likewise, you would take B complement, complement. If you think about these operations, if you have B and take B complement, it's the opposite. So if I take the complement of B complement, it ends me back up at B. So this operation really undoes itself. And this is the same as finding A intersect B. This is a whole lot easier to find than dealing with all of these operations at once. So it's really, really helpful for us overall, okay? So what I'm going to do, again, you can show that these are true exactly in the same manner as the last problems. You can see the region that it talks about just in a Venn diagram with two sets. But what we're going to do is we're going to just apply it to a specific problem, and you're going to see we get the same thing either way. It really doesn't matter. So we've got the set U, which is the letters A through J. Then we've got A and B. And what I want to do is I want to find A union B complement. So the first way I'm going to do this is with a Venn diagram, because this is a method that you're used to. So let's find the set and make sure we know how to do this. So I go ahead and draw my universal set. And then I've got my two sets A and B. Starting out in the middle, A is common to both, G is common to both, and I is common to both. So those three letters have to go in there. So let's cross those off from you. A, G, and I have found a home. Then moving into A circle, E and H are left. So those go here to the side. And then in B circle, the only thing that remains is J. So that goes here. And then I've got a few other pieces. B, C, D, and F have not found a home. So those all go on the outside. Okay. So if I want to find this set, I've got to start by finding the union. So if I look at A union B, we'll go ahead and list that set out. That melds these two circles together. So A union B would be all these letters. Again, it's up to you how you go about this. trying to look at this and put it alphabetically right now, that's a little hard for me. So I'm just going to list it by section. So E, H, A, G, I, and then J. But now I'm going to put it alphabetically because that's just going to help me when I have to cross stuff out. So my first letter is A. I don't have B, C, D. E is next. F. And then we've got G, H, I, and finally J. Okay. So those are the letters alphabetically. Now what I want to do is I want to take the complement of this. Okay. So that would just be everything not shaded, which ends up being the outside. So this ends up resulting in B, C, D, and F. Okay. If again you don't like Venn diagrams and you want to use just the sets themselves, what I would do from A union B is I would cross off those letters here. So A is in this set, E is in the set, G is in the set, H, I, J. And so my complement is the stuff that hasn't been used, B, C, D, F. Okay. So that is our ending set. Okay. Now I'm going to do this using De Morgan's law just to show you, you get the same thing. So I need to find A union B and then take the complement. Instead, I can distribute that down. So you take A complement, B complement, and then the operation has to flip to the intersection. And I can still use the Venn diagram for this. Venn diagrams are always helpful for just visualizing everything. If I start by listing A complement, I go ahead and cross that circle out. And what's left is everything on the outside plus J. So in order, that would be B, C, D, F, J. Then we do the same thing with B complement. Ignore B circle. And that leaves me with E, H, B, C, D, and F. So this one's not too bad alphabetically. B, C, D, E, F, H. Now I'm looking for the intersection of these two. So the things that are in common are B, C, D, and F. So indeed, you end up with exactly the same thing, okay? If you want to do the shading, just to show you this, if you take A complement, that would be all of this stuff. B complement is all of this stuff. So when I take the intersection, it's just where the shading overlaps, which is only on the outside. So again, results in exactly the same thing. Okay. So we got one last thing we're going to do in this section, and that's going to be, again, to try to apply these set operations to describe a very specific set. So if these are my regions, the first problem I'm going to do is I want to figure out, can I come up with a way with my operations to talk about region 6? Okay. What I'd recommend doing is trying to verbalize what the elements are that are here. So if I give a description, if I look at region 6, it's inside circle C and it's inside circle B. So these elements are in B and they're in C. However, B and C would be these two things. So they're in B and in C, but they're not in a circle. It excluded that. So they're in B and in C, but are not in A. Okay. Now we usually use the phrase but that doesn't equate to an operation. So another way you could say this is they're in A and they're in C and they're not in A. Or sorry, they're in B and in C and they're not in A. Okay. So the way I would need to write this is take it piece by piece. If they're in B and C, that means they're in the intersection of these two sets for sure. Okay. The end here then tells me take the intersection as well. And then we've got not in A. That means they're not in A. So they're in a complement. Okay. So you can take that phrase and just translate it to the different operations. Okay. So these elements are in B and C and they're not in A. So they're in a complement, which would be everything on the outside. So it's finding the overlap between those. Right. So let's try a second one of these. Let's figure out how I can talk about the stuff that is unique to one region. And we'll just do A. Okay. So if I think about these elements are in A for sure. But I need to exclude the stuff that's in B, and I need to exclude the stuff that's in C. So they're in A, and they're not in B, or C. Okay. The other way you could write this is they're not in B, and they're not in C. So this is method 1 to write this, and this is method 2. And I'll show you, they really end up being the same thing. So a second way to say this is these elements are in A and not in B and not in C. So give it a little space so this way I can actually write this set down. They're in A, so that means I definitely need to write that they're part of it. And tells me to go ahead and put an intersection. And then not in this set. Okay. So B or C would be the union. And then they're not in either one of these. So I would take the complement. So that's one way I can go about this. So B union C would be these two regions. So these elements are definitely in the complement of that overlap with a circle. Again, the second way I could write this is they're in A. And they're not in B. So that means B complement. And would indicate another intersection, not in C. So that gives me C complement. Okay. And so really this just results from De Morgan's law. You can distribute that complement down, and then it would just flip the operation to intersection. Okay. So it all depends just how you write it, how you would translate it. But again, you have tons of different ways that you can talk about these particular sets. Right? So your homework is going to have a lot more problems that you need to actually find these set operations and list the elements that are in there. But we've just done it in a more general sense of, if I take this operation, this is the region, and I would write all those elements in. So again, otherwise, try not to make these videos 2 hours long for you. But if you have any questions, let me know.